Hello, in this presentation I want to describe the approach that we've created for the more agile and simpler specification of code generators. Now, code generation is a very key element of model-driven engineering whereby systems are defined as models and executable code is generated automatically from those models by a code generator. So the code generator reduces, in principle anyway, the manual effort of producing a system very substantially, and production of code can be much accelerated by means of code generators. For example, we could specify a mobile app by a platform independent specification and then generate the Android and iOS implementations of that app automatically, and that involves the production of a very large amount of elements that are needed for those platforms which don't need to be specifically described in the specification, but they're there to enable the implementation. So code generation is very important and potentially very beneficial, but the actual writing of code generators is an expensive task, and it needs very deep understanding of the languages involved. And it looks like these typically cost several person years to develop. If we look at some code generators like the icsea UML to Java code generator, which is on Eclipse, that took multiple person years, 3 at least person years. My own experience of writing UML to Java or UML to C++ code generators, UML to C code generators, or UML to Python code generators, again, these are at least 1 person year and couldn't be more than that. So we need to reduce that cost because programming languages are multiplying in the present time. We've seen new languages like Kotlin and Swift introduced for mobile platforms. There are other languages being introduced for specialized purposes. Inevitably, there will be a need for new code generators and variations on existing code generators to deal with the changes of versions. For example, Swift has gone through 5 versions to date, which are quite different languages in some cases. Well, look at the use case for producing mobile apps. We could write a specification, as I said, in a platform-independent way in UML, and then generate the code for that in Android, for example, using Java, possibly Kotlin as well, and for iOS. And again, within iOS, there are different platform variations. You can have Swift. Swift UI is the latest approach, but there are other approaches as well. There's Objective-C based apps in iOS as well. Now, one approach that we've used to reduce the effort of writing code generators is to break down the code generation process into several stages, so that we start with a UML specification, then that's produced, from that is produced a design which is closer to an implementation but is still platform independent, and this uses, for example, pseudocode, algorithms, and ideas like caching, but they do it in a platform independent way. And then to have meta models and intermediate representations which are geared towards particular families of languages. For example, static type OO languages are one big family. Procedural languages could be another family. Dynamic type languages another family. So this means that the new code generators are essentially at the final step, and we wouldn't expect much changes in the earlier code generators. Now that works in general, and that does reduce the effort, but we'd like to go a bit further. Now, what does code generators production consist of? It consists of defining a valid representation of the source language and the target language. In other words, identifying what should the code generator actually do to generate code, what should be the representation of, for example, a UML class in the target language. Define the code generation strategy to produce that representation, and then to write and test the code generation rules. Now, where are those code generation rules written? This is the big question. We can write those code generation rules themselves in a 3GL like Java, or we can use a specialized code generation languages, which the main ones that are available are template-based languages. So abstract syntax to abstract syntax is one code generation approach where the code generation rules are written in 3GL or a model transformation language, and this represents the source model, for example a model in UML, as a model of the target language, and then actual text or strings are produced by a printing routine defined on the target abstract syntax. To do this, you have to know both abstract syntaxes, both metamodels. That's quite advanced and specialized knowledge, and is very time consuming. More often, the current, probably the mainstream way of writing a code generator is abstract syntax to concrete syntax, which means that the code generation code is written in templates using the target language, in the actual literal target language, with variable parts or slots written in the source language abstract syntax. And these are the languages like the Epsilon generation language EGL and icsea, which are based on template structures. Now, what we suggest in this presentation is instead to go concrete syntax to concrete syntax, where we write rules where they're expressed in terms of the concrete source language and concrete target language, and there isn't any need to be aware of metamodels. What do some of these code generators look like? Here's an extract from a Java code generator which does UML to Java. It produces string output. It takes in this case, a basic expression. This is query form defined on the class basic expression, and it produces text based on what is the operator of that basic expression, and so on and so on. Very, very large bits of code. We're talking thousands of lines of code and years of production. The EGL or icsea approach instead has concrete syntax templates. As you can see here, the concrete syntax is written in the target language, in this case Java. This is going to be printed out as a literal string, public class basic Boolean expression. And then the actual template elements at the abstract syntax level include these insertions, which are variable based on the source language element, in this case a state machine transition. So this is going to vary depending on what the name of the transition is, what the name of the state machine is. Now you can see here this involves the use of delimiters. There's a square bracket percent square bracket, delimit the literal concrete syntax of the target from the abstract syntax of the source. That, of course, can become quite confusing, and for more complex functionality, the coding here can be, again, very complex and difficult to understand and to maintain. So what we propose is something a bit simpler and something that's more usable by people who are not MDE experts. So what we do in CSTL, or Concrete Syntax Transformation Language, is to write rules where the left-hand side is concrete syntax in the source language, in this case a little bit of OCL, and the target is concrete syntax in the target language. So here what we say is replace this left-hand side, replace the left-hand side, which has the form something and something else, by something and something else. In other words, a single and is replaced by a double and, or operator is replaced by the programming language or operator, and so on and so on. It can become quite complex. For example, in the source language we might have less than to compare strings, but that might not be present in the target language. Instead, we have to use some other operator like compare to operator. Or equality of two sets. In the mathematical equality sense, that has to be implemented by a special purpose routine, which is defined in a supporting library. Now, this is much more concise. It's about a factor of 10 more concise than either of the previous approaches. And unlike the abstract syntax or concrete syntax, abstract to abstract or abstract to concrete approaches, we don't need to know any abstract syntax knowledge. So generally our experience of building large code generators in Java and OCL convinced us that we needed to have a more usable, agile and lightweight approach. And so over the last couple of years we've defined this CSTL and we've used it for real applications as part of a UML2 app implementation. It's a scripting language. It is interpreted, which you might expect to have an impact in terms of efficiency. However, we found the efficiency was of acceptable level. So individual rules have a source element, concrete syntax in the source language, mapping to target element when a condition is true. The when and the condition are optional. The LHS is concrete syntax in the source, RHS is the concrete syntax and target, and we can have variables or meta-variables which represent abstract concrete syntax and their translations. Written on the left-hand side it's the source element and on the right-hand side it's the target. We group the rules into source language syntactic categories and they're ordered by specialization. So for example, UML to C, we have integer mapping to int, real mapping to double, boolean to unsigned car, and so on. Of course, this can be changed very quickly if we decide that we don't want to represent a set by a pointer to the thing that's the set of. Classes are represented as structs, inheritance represented by the first member of the struct being a superclass pointer. That translates this class into that struct. We can use stereotypes of left-hand side model elements as conditions. So we can say if something is if an attribute is read-only, then in Swift it gets translated to a constant. We can also modularize these specifications by having multiple files, each file representing a particular kind of translation, and we can invoke that translation by the backquote notation. So if we want to translate a variable by a specialized kind of translator, we say backquote f.cstl for the translation by f. For example, having separate header and code body translations for C. Now our main applications have been for app synthesis, where we've written code generators for Java 8 and for Swift 4.5. We also provide the translator as part of Eclipse Agile UML toolset. Here, for example, are some rules for the Java 8. And the evaluation, our existing Java-based translator for C++, and indeed Java, has around 20,000 lines of code, whereas the CSTL is around 500, less than 500 lines of code. Even the template-based approaches like the icsea20Lano translator that you can find on Eclipse is 4,000 lines. And it doesn't even generate detailed behavior, it generates just outline method bodies. The EGL approach is a bit more concise, but still around 3 times larger than ours in CSTL. Here's an example. Let's have a look at it in the toolset. This is an example of the icsea model, which features various elements of UML. Can type check our specification, and if we want to use a particular CSTL file, then we say use that CSTL file. That then appears in the output, and we get the generated Swift for that, or whatever language the CSTL file is implementing. And as I say, in terms of efficiency, the efficiency is not too bad, and indeed is actually better, even with this the interpreted CSTL. It's better than the implemented icsea for the same models. The real gain, though, is in development effort. As I say, these large-scale code generators typically would take multiple person years of effort, whereas we found that the CSTL versions would be instead in the matter of person months. Now, of course, this can be enhanced with various ways. You could further potentially automate code generation construction by using machine learning to learn what are the text-to-text mappings. But probably many examples would be needed, and the disadvantage there is that using, for example, a neural net approach, the result is a black box where we don't have explicit rules to say what is the mapping actually doing, but we have to take on trust that the machine learning has learned the right thing. Other approaches are sketch-to-code approaches, where UI sketches can be converted into UI code, and this seems like a very promising approach to reduce coding time for UIs. And there are also template-based or data-based approaches for apps like Power Apps or AppSheet. But these have very narrow range of functionalities that can be produced, as opposed to a full model-driven development approach where, in principle, almost anything could be specified in a UML model. So, in conclusion, we've introduced CSTL. It's a declarative scripting language, and it enables us to write code generators in a much simpler way than the previous approaches, templates or 3GL coding, and it can also produce more efficient code generators, even though it's a scripting language, and it can reduce substantially development and maintenance costs. Thank you very much. Any questions, please send me an email.